that atoms, as we know them, weren't really atoms. What if you could just strip away everything else, the fuzzy electron cloud, all that space it takes up, and just look at the incredibly tiny, dense core? What would actually be left? That's a really fascinating concept we're diving into today, and it's based on the material you shared with us. It explores this, well, extreme state of matter where atoms lose all their electrons, leaving just the bare atomic nucleus behind. So our mission in this deep dive is to explore this pretty radical idea, understand what a bare nucleus actually is, then figure out how these bare nuclei would differ from each other, and what strange, almost alien properties they'd have compared to the, familiar atoms that make up our world. We're looking at an analysis that compares different elements in this completely stripped-down state. Let's get into it.
Yeah, it's fascinating, isn't it? How profoundly matter changes when you take away that electron cloud. Basically, a bare nucleus is just the protons and neutrons packed tightly together right at the center of what used to be an atom. Well, except for hydrogen, of course. The most common kind just has that single proton to begin with.
Right. And when that electron cloud disappears, the changes are pretty dramatic, aren't they? It's not just like a smaller atom. It's something fundamentally different.
Oh, completely different. The first and maybe the most striking change is the total loss of chemical identity. Think about everything we associate with elements. Is it reactive? How does it bond? Its color. Is it a metal, a gas? All that stuff. That's all determined by the electrons. So you take those away and poof, that familiar identity just vanishes.
So bare gold wouldn't look golden. It wouldn't even be metallic.
Not in the slightest. A bare gold nucleus is just, well, a specific collection, 79 protons and a certain number of neutrons. Without the electrons there to interact chemically or, reflect light in that specific way, its familiar properties are gone.
Right, because chemistry is all about electron interactions.
Yeah.
And then there's the charge aspect.
Exactly. With no negatively charged electrons left to balance the positive charge of the protons, that positive charge is totally exposed. There's no shielding anymore. It's just raw positive charge.
And here's where, for me, it gets really interesting, the sheer size difference. We think of atoms as tiny, right? Picometers, angstroms. But that size is essentially defined by the reach of the electron cloud.
Yes, precisely. But the nucleus itself, that's on a completely different scale. We're talking femtometers. That's 10 to the minus 15 meters. An atom, including its electron cloud, is roughly, get this, 100,000 times larger in radius than its nucleus. So the atom is mostly empty space, and it's the electron cloud that dictates its apparent size. A bare nucleus just gets rid of all that space.
Okay, wow. So strip away the electrons, lose the chemical identity, get this fully exposed positive charge, and the object shrinks down to this incredibly dense, unbelievably tiny core. So if the chemical differences are gone, how do we even tell one bare nucleus from another? What's left? What gives them their identity now?
That's the key question, really. And it shifts the whole perspective from chemistry to, well, nuclear physics. They're no longer differentiated by how they bond or react, but by the intrinsic properties of that central core itself. The most fundamental difference is still the atomic number. We call it Z.
Z, right, the number of protons. So that count still defines the element even in this bare state.
It absolutely does, and it directly dictates the electric charge of the bare nucleus. It's always fixed at plus Z, where E is that fundamental unit of charge.
So a bare hydrogen nucleus, that's just a proton, right? So plus 1 e charge.
Correct.
Bare helium, which I guess you mentioned is like an alpha particle, that's plus 2 e.
Exactly. An alpha particle is a bare helium nucleus.
And bare uranium. Wow, that would be a staggering plus 92 e charge.
It would. And how they'd interact with each other would be totally dominated by that massive positive charge. Just intense electromagnetic repulsion, pushing each other away very, very strongly. Now, inside each nucleus, you still have the powerful, strong nuclear force holding the protons and neutrons together. And the weak force is still around, potentially causing decay. But gravity, at this scale, it's basically negligible.
Okay, so the number of protons sets the charge and the fundamental identity, hydrogen, helium, uranium, whatever. What about their actual stuff, their mass? How does that vary between bare nuclei?
Good point. That difference comes down to the mass number A. This is the total count of everything in the nucleus, protons plus neutrons. So Z plus N bare nuclei differ in mass based on this total count of nucleons.
And this isn't just different between, say, a bare carbon nucleus and a bare oxygen nucleus. It could be different between isotopes of the same element too, right?
Exactly right. Take carbon, for instance. Carbon-12 has 6 protons and 6 neutrons. Mass number A is 12. But carbon-14, still 6 protons, that's what makes it carbon, but it has 8 neutrons, so its mass number is 14. So if you have a bare C12 nucleus and a bare C14 nucleus side by side, the C12 one is distinctly less massive. Even though they're both carbon nuclei because they both have 6 protons, their mass is approximately A times the atomic mass unit.
That makes perfect sense. More neutrons means more mass, even if the charge is the same. Okay. Now, is this core stuff always stable? Or do some of these bare nuclei just fall apart on their own? We know some atoms are radioactive. Is that property something tied to the electrons, or is it inherent to the nucleus itself?
That's a really great question, and it gets to another key difference, nuclear stability and radioactivity. And this property, it's entirely intrinsic to the nucleus itself. It has nothing to do with electrons that might have been there. It depends completely on the specific combination, the specific mix of protons and neutrons within that core.
So a bare C14 nucleus would still be radioactive, just sitting there on its own.
It would.
And a bare U-238 nucleus would still undergo decay.
Precisely. A bare C14 nucleus, because of its particular proton-neutron ratio, is unstable. It would still undergo beta decay. That's where one of its neutrons essentially flips, becoming a proton, and it spits out an electron, well, what would become an electron, and a tiny particle called an antineutrino. And a bare U-238 nucleus, still alpha radioactive. It naturally sheds a chunk of itself specifically. It emits an alpha particle, which, as we said, is just a bare helium nucleus, 2 protons, 2 neutrons. So they would definitely differ in how they decay and also how fast they decay, and that's purely based on their internal nuclear structure. Stable bare nuclei like, say, hydrogen-1, helium-4, carbon-12, oxygen-16, they just remain stable.
That's fascinating. So their fate, in terms of decay, is kind of pre-written within the nucleus itself. What about other, maybe more subtle properties? Quantum properties? I've heard about nuclear spin. Is that still a thing for bare nuclei?
Oh, absolutely it is. Protons and neutrons, just like electrons, have this fundamental quantum mechanical property called spin. You can sort of picture it like a tiny top spinning, though, the quantum reality is a bit more abstract than literal rotation. And depending on how the individual spins of all the protons and neutrons add up within the nucleus itself can have a net overall spin.
And if it has a net spin, what does that mean?
Well, if a bare nucleus has a non-zero spin, it also possesses what's called a magnetic moment, like a tiny bar magnet. This means it can actually interact with external magnetic fields. This intrinsic property is actually what's exploited in techniques like nuclear magnetic resonance, NMR. MRI in medicine is based on this. It probes the structure of materials by seeing how atomic nuclei respond to radio waves when they're sitting in a strong magnetic field, though usually that's done with nuclei still surrounded by their electrons.
Got it. Okay, so we're building a picture here. A bare nucleus is defined by its core properties. Proton number, giving its charge and element type, total mass number, determining its mass and isotope, its own intrinsic stability or radioactivity, and potentially things like spin and a magnetic moment. But, as we know, this state is incredibly rare, certainly here on Earth. Why don't we just find these things lying around? What's the catch?
The catch is the energetics. It's the practical reality. Creating these bare nuclei, especially for elements with lots and lots of electrons, requires just an enormous amount of energy. You have to overcome what are called the successive ionization energies to rip away every single electron one by one.
And it gets harder with each electron you remove, doesn't it?
Significantly harder. As you pull off electrons, the remaining ones feel a stronger pull from the increasingly positive charge of the ion that's left behind. They're held much more tightly. So the energy needed to remove, say, the 10th electron is way more than the 1st, and the 50th is way more than the 10th, and so on.
So for something heavy like uranium, with its 92 electrons, pulling off that very last one must take unbelievable amounts of energy.
Oh, the energy required to create a truly bare uranium nucleus is just astronomically high. It's far, far beyond what's feasible in any typical laboratory setting, certainly not for making any significant amount of this stuff. We do study highly charged ions, HCIs, where many, maybe even most electrons are removed. That's a whole field of research. But getting them completely bare for heavy elements, that's a monumental challenge. It's much easier for lighter nuclei, of course. Hydrogen just needs 1 electron removed. Helium, 2. So those are much more readily studied in a fully bare state.
Right. Okay. Theoretical exercise time then. Let's say you could somehow gather a large group of these bare nuclei together. What would that even be like? What state of matter are we talking about?
Hmm. Okay, well, it would technically be an extremely exotic state of matter. You could call it a form of plasma, maybe, since plasma is usually defined as an ionized gas. But this would be a very peculiar, purely nuclear plasma, completely devoid of the electrons that are usually swimming around in the plasmas we're familiar with, like in lightning or neon signs.
And trying to actually squeeze them close together. Would that
Yeah.
be possible?
That's the huge challenge. You might think, okay, ordinary matter is mostly empty space because of electron clouds, so maybe you could compress these tiny bare nuclei to incredible densities. But remember that intense positive charge. The electrostatic repulsion between all those concentrated positive charges would be absolutely overwhelming. They had to fight incredibly hard against being pushed together. To force them close enough to actually overcome that repulsion and reach densities like, say, the density inside the nucleus itself, which happens in extreme objects like neutron stars, you'd need truly immense forces, like the kind of gravity you find in those collapsed stars.
Wow. Okay. So bringing this deep dive towards a close, what's the kind of core insight, the main takeaway from exploring elements stripped completely bare like this?
I think the key takeaway is realizing that when you remove the electrons, the identity of an element, all its familiar characteristics, reduces entirely to the properties of its nucleus. That's it. Its charge, which comes directly from the number of protons, Z. Its mass, determined by the total number of protons and neutrons, A, which also tells you about isotopes. Its inherent nuclear stability or radioactivity. And its fundamental quantum properties, like nuclear spin. Everything else is gone.
It completely bypasses the familiar periodic table, doesn't it? Because that whole table is built on electron configurations and how elements react chemically.
Exactly. That becomes irrelevant. The relevant map, if you will, becomes something different, like the chart of nuclides.
Hmm.
That chart organizes all the known nuclei, not by chemistry, but by their proton number and their neutron number. And it shows you which ones are stable, where ones decay, and how they decay. It's a nuclear physicist's periodic table, in a way.
And while making this stuff here is incredibly hard, you mentioned that states approaching this level of ionization, or even achieving it, do exist out there in the universe.
Oh, yes. You find conditions where atoms are fully ionized, stripped bare, in truly extreme environments, like the cores of stars, due to the unbelievable temperatures and pressures. Everything is just plasma there. And also, cosmic rays. These are highly energetic particles zipping through space, originating from supernovae or other violent events. Often, these cosmic rays are just bare atomic nuclei that have been accelerated to near light speed.
Okay, so for you listening to this deep dive, just take a second to think about this. Our entire everyday experience of the material world, the colors we see, the textures we feel, how things react chemically, even the strength of a piece of metal is almost entirely defined by those outer electron clouds surrounding the nucleus. It's dictated by things external to that tiny core itself. This material we've looked at really shows us that beneath that familiar electron-governed world, there lies this hidden, fundamental reality of matter, one defined purely by the nucleus, governed by completely different forces and rules, the strong and weak nuclear forces, mainly. How different would the universe actually seem if our senses, or our primary way of interacting with matter, operated at that nuclear level instead of the electron level we're so used to? It's hard to even imagine. And it makes you wonder what other fundamental properties or layers of reality might be hidden beneath the ones we can easily perceive or manipulate day to day. A really mind-bending concept. Thank you for providing the material that let us explore this fascinating deep dive, and that's the end of this deep dive.